Hello and welcome to Degrees of Freedom, mixing solid, shell, and line elements in Nastran and CAD. My name is Robert Smith, Mechanical Solutions Engineer for Hagerman & Company. The goal of today's presentation is to shed light on the concept of degrees of freedom as it relates to finite elements. I'll start off with a little fun in PowerPoint, where I will thoroughly confuse you. Then I'll jump into Nastran and CAD and demonstrate some of these concepts, hopefully making sense of things. Although I'll be using Nastran and CAD, this concept is something that anyone using any FEA program should get a grasp of. I suspect it's little known and little understood by designers and engineers who aren't expert analysts, but only employ this technology part-time. Anyone who's been in any of my training classes may have seen me struggle to explain these concepts on the fly, as training materials rarely discuss degrees of freedom. I remember learning this stuff myself, and topics like this were often described by help documentation in ways that were less than helpful. We can't talk about degrees of freedom without talking about the element. Many of you probably already know what I mean when I say element, but let's review the terminology real quick before we move on. I'm not going to start quoting Wikipedia definitions here, nor am I going to elaborate much on the finite element method itself. If you want to review the basics of FEA, check out our blog or our YouTube channel for a presentation called Inventor Stress Analysis Basic Theory. I cover the fundamental strategy of FEA, which includes the role of elements in the process. In short, the finite element method is a process for predicting the behavior of physical systems that are too complex to represent mathematically. We do this by rebuilding the complex system using lots of simple systems, which do have equations that govern their behavior. In other words, we take a complex problem, break it into lots of simple problems. We assemble all of those simple problems and solutions together to approximate the solution of the big problem. The building blocks of FEA, the simple problems, are called elements. They come in many shapes, they apply different mathematical theory to represent different kinds of physical objects. Some are more generic in their use and some are very specific. They all have rules that govern their proper use, and if misunderstood, their behavior can be anything but realistic. When you start talking about element types, you can speak broadly about their geometric form factor, and you can get a lot more specific with actual element names. For example, the most commonly used element type is the solid element, an example of which is the linear tetrahedral. Also a solid element, however, is the parabolic tetrahedral element and the hexahedral element, known as a brick to you sim mechanical folks. Then there's the shell elements. We'll find shell elements in quadrilateral and triangular shapes, and they also come in a linear and parabolic variant. The line elements are always just lines geometrically, but could be beams, bars, pipes, springs, rods, or cables, and that's just in Nastran and CAD. Simulation Mechanical, for example, had even more line element types. They all have their uses, and they all accept different inputs and deliver different outputs. This presentation would take up the better part of the day if we were to discuss each one of the elements in detail. When we're talking about degrees of freedom, though, we don't have to. In general, the degrees of freedom supported by the solid elements are the same, whether they're tets, bricks, linear, or parabolic. The shells have their own degrees of freedom, which are generally consistent from element to element, and beams, bars, and pipes will behave the same way as well. In fact, these rules are not product-specific. These rules are applied universally in FEA. And the concepts we discuss today will apply in any product. Some products may support additional elements and options that build on these concepts, but they all use these three basic element types in the same way. Okay, so what is a degree of freedom already? Well, degree of freedom is not a phrase that's exclusive to FEA. You'll hear that terminology in CAD modeling when you're talking about constraints, whether those constraints are in the 2D sketching environment or constraints that hold the components of an assembly together. You'll also hear it when kinematic systems are being described, or even in statistics. The most basic definition is that a degree of freedom is a variable, or a parameter, that can vary. In terms of CAD constraints and kinematic chains, the variable is position. When we describe position in 3D space, we use coordinate systems. Here we're looking at our good old friend, the three-dimensional rectangular Cartesian coordinate system. Of course, there are other systems, like cylindrical or spherical systems, that are commonly used in FEA, but we'll stick with this convention for today. In this coordinate system, it can be stated that a completely unconstrained object has 6 degrees of freedom, or in other words, 6 possible ways that it could move. It can translate or move along the X, Y, or Z axis, or it can rotate about the X, Y, or Z axis. 3 translations, 3 rotations. If we were to constrain an object from moving in any way, it could be said that we are removing degrees of freedom. In FEA elements, the degrees of freedom are controlled at the corner nodes. The nodes are the black spheres in my little models. I've exaggerated them for visual clarity. In structural FEA, nodes serve three main purposes. They're the locations to which we apply loads, like forces and temperatures. Nodes are where the solver reports results back to us. And nodes are where we constrain the movement, or displacement, of an element. Our basic building blocks for highly idealized structures, the bar, beam, and pipe elements. These guys are great for representing long, uniform cross-section structural members. Why mesh a beam with thousands of solid elements when there are textbook formulas governing their deflections? Use just a few line elements, also known as 1D or one-dimensional elements, and you'll get good results at a fraction of the cost. The only difference between the bar and the beam in Nastran in CAD is that the beam allows you to offset the neutral axis from the actual line that's drawn in the CAD model. Pipe elements support internal pressure, which can affect their stiffness. All of these elements support all 6 degrees of freedom, so there isn't much to think about when working with strictly line-based models. By the way, each node has degrees of freedom, even though I've only shown the triad on one of them. Here's where things start to get a little confusing. The solid element, the most commonly used element out there, does not support all 6 degrees of freedom. Yeah, solid elements only support translation. There are no rotational degrees of freedom. The meaning of a missing degree of freedom in FEA is a bit different than its meaning elsewhere. When an FEA element is missing a degree of freedom, it doesn't mean that it's not free to move in that direction. It means we can't control it in that direction. A node on a tetrahedral element is free to rotate in any direction, but we can't constrain it from doing so. Also, we can't apply a load, such as a moment, to the node that would force it to rotate. You may have been using these elements for years and not known this, and that's because often it doesn't matter. Hopefully I'll make a little more sense out of that when we get into the software. The shell is a little funky too. The default shell elements only have 5 degrees of freedom. The one that's missing is the rotation around the axis normal to the shell surface. This is often referred to as the drilling degree of freedom. If you picture a drill punching a hole through the surface, it's the rotation of the drill bit. Now, there is some stiffness supported in that direction. This is just so shells can be connected together out of plane, like perpendicular to each other, and still transmit forces to one another, but it's not a true degree of freedom that you would directly apply a load to. Notice the nonsense I've written below my table there. Those are the element names in Nastran speak. All of the elements we've discussed have specific names that the Nastran solver understands. In the case of the Nastran in CAD product, you don't have to know these, and they're typically hidden from you. C-quad 4 and C-quad 8 are the 4-sided shells, linear and parabolic respectively. The number on the end corresponds to the number of nodes. C-tria 3 and C-tria 6 are the triangular variants. So why do I bring this up? Because there is a shell element in Nastran that does have all 6 degrees of freedom, and the dialog box where it's activated does list the elements by name, so I wanted you to understand what it was talking about. The C-quad R and C-tria R support all 6 degrees of freedom. This is common in other products as well. Either there will be a specific element that has the drilling degree of freedom, or an option to activate the drilling degree. So if you're going to apply a load, such as a moment or a rotation in this direction, be sure to use the element that supports it. Now, let's jump into the software and demonstrate this stuff. Now that you know the basic rules, let's see how they actually affect the models. Okay, here we are in Autodesk Inventor, and we're going to be looking through a very simple model that is already set up in the Nastran in CAD environment, so we'll launch that now. So what we're looking at here is a solid block that's meshed with solid tetrahedral elements. Attached to that is this plate-like structure, which is meshed with shell elements. If you've never used these before, you can see that geometrically there is no thickness to this structure. It really is just a surface in the CAD model. But what happens is the shell element contains information about how thick that plate really is and what it's made of. So both of these are controlled with what they call idealizations in Nastran in CAD. So the solid block, if I look at that, I've got an idealization that's telling this part in the assembly to be meshed with solid elements and be made of steel. And then the other idealization I have in this model is basically telling that part in the assembly that it's going to be using this shell element and that it's going to be made of steel. But also, how thick is that plate structure that I'm trying to simulate? So in this case, 0.01 inches. So even though geometrically there's no thickness to this structure, it's going to behave like a steel plate of thickness 0.01 inches. As far as the setup of the model, I've put a force on the very end of the plate structure, just 1 pound in this case. Okay, so you can see it's in the negative y direction on that front edge. On the bottom of the solid block, we have a constraint, which is constraining that whole face to be fixed. Something that should be pointed out in the constraint dialog here, and this is, at least in my experience, common in all FEA products. They're not going to tell you what degrees of freedom are actually supported by the structure that you've selected when applying a constraint. Notice in here I've got 6 check boxes for each of the degrees of freedom, and it's not telling me that the RX, RY, and RZ are going to have 0 effect because I'm using solid elements. They're still present. I can still check them and uncheck them. They're just not going to do anything. It doesn't hurt anything either, but it'll never be clear to you inside the dialog box what degrees of freedom are supported by your element. That's something that you need to be aware of yourself. And the two parts are bonded together with a bonded contact. So what I would expect by applying a load on the end of my shell mesh plate structure there would be bending, right? Kind of a cantilever situation we'd see going on there. So let's run it and see what we actually get. Okay, and what we get is an error. Nastran solution failed. And when I hit OK, the little output log goes away, but I can bring that back, scroll down, and see exactly what the fatal error I received was, and that is a singularity detected at grid blah blah blah. And what that basically means is I have an under-constrained model. I have a model that is not in static equilibrium and so cannot be solved by a static solver. And that's Nastran's way of telling us that. Different codes will have different jargon that say the same thing, so you'll see that message eventually if you run Nastran and CAD for any length of time. So what's really happening there? Let me just finish the environment, go back to the modeling environment for a second to see if we can illustrate what's happening there. Suppress a constraint, that should allow me to move this. Okay, so what's happening? The shell structure is joined to the solid structure at one edge. Applying a force on that edge tends to push the plate down and causing rotation. I expected bending because I expected that the rotation would be resisted where the plate structure meets the solid. And that's not happening because the solid tetrahedral element does not support rotational degrees of freedom. I cannot resist the rotation that's imposed by the force I put on the end of this thing. So what I get is a situation like this. Okay, there is a load that is not opposed by an equal and opposite reaction force, so it's not a static problem. Essentially, the plate is spinning infinitely, and I do not have a solution. I have an error. Let's go back into Nastran and CAD environment. Okay, and let's go to another, what they call subcase, that I have set up in this particular model. So subcases are different sets of loads and constraints that you can apply to the same geometry and the same analysis. And I've treated this a little bit differently. They're still meshed in the same way. They're still joined together with a bonded contact. But this time I've put a fixed constraint on the end of the plate structure. So with a fixed condition on that part and a fixed condition on the solid block, No matter what, I know I'm going to get a static problem, but it still may not behave exactly like I expect it to. This time I've applied a pressure to the underside of that plate structure, just a uniform 1 psi pressure. Okay, now we have a completed solution. Let's take a look at the results that it gives me. We'll just look at displacement. Okay, so I do get results, but I don't get bending like I expect. Well, what do I mean by that? If we look at the end where the plate structure is fixed, and let me get this animating so it's a bit more clear. But because the shell elements on the plate structure do support rotational degrees of freedom, when I fixed them with my constraint, it's not allowing rotation at that end. So what I get with the pressure applied underneath is bending. On the other end, where the shells connect to the solid, I do not see bending. I see basically a hinged condition. Again, because those solid elements do not resist the rotation. It still works, it still gives me results, but it doesn't give me good results. And I need to understand why, and hopefully after watching this presentation, if you get a condition like this, you'll understand what's going on there. So you can see the difference between this end and the bending, which I expected to see on this end. Okay, so let me switch to a model where the plate structure is not meshed with shell elements, but instead solid elements, and show you that why, if you've been using with solid elements for years now and this has never happened to you, why it typically doesn't matter, and a lot of times you can just move on with your life and not think about degrees of freedom. So we've got what is more common in a lot of people's models. All of the parts are meshed with solid elements, and when they're bonded together, we have more than one node making contact between the two parts. In fact, there's at least 3 nodes connecting a solid part to a solid part, and those 3 nodes are not in line, so we don't have a hinge condition. We have enough nodes that are resisting translation only to prevent this whole plate structure from rotating. You would still see the same condition if you had modeled your 3D model like this, right? Because all of the nodes connecting the parts together are in a line, and none of those nodes are going to resist rotation, so I'd get the same problem on this end. I'd get a hinged condition, I'd get really a non-static problem and a failed analysis. But this is uncommon, right? In our assemblies, typically it's going to look more like this. This might occur, if it's a sharp corner making contact with a plate, or maybe you've cut a fillet in something to prep for a weld and it's only making contact on the edge. You might see something like this, and that would cause the hinged condition, that would cause you problems. So if you see that, hopefully now you'll be aware of why you're getting errors or why you're getting odd results. But again, non-typical, so a lot of times if things are modeled this way, it's not going to matter. It's not going to exhibit any problems. So if you are getting problems, and typically this is when we're mixing element types, as I did in my first model, there's a solid element versus a shell element. That's really when the degrees of freedom start to rear their ugly head if you're not aware of their behaviors. So if you are mixing models, how do you get around that stuff? How do you fix those problems? There's a few ways to approach it, and it depends on the model, of course. But look what's been done here. A lot like the second model I did, where everything's meshed in the same way, shell, solids. I do have a fixed condition on the end of the shell, right? And the two parts are bonded together, and there's a pressure on the underside of the shell. But in this case, the shell structure is overlapping the solid structure such that they're not meeting at a single row of nodes, not a single edge. So there's at least 2 rows of nodes, or at least basically three nodes that are not in a line connecting these two parts together. So we don't get that hinged condition. Free rotations don't really matter anymore. It's all going to be converted to translations at each one of those nodes, and I will get the results I expect. Let's give that a run and confirm that. All right, solution complete. We'll animate our displacement results. And sure enough, I get the bending that I expected on both ends. Now in this other model here, I've just shown a few other ways that you can deal with that. Let's say this is a condition such as this, where a plate meshed with shell element is going to be meeting up with the face of a solid structure meshed with solid elements. There's no way that I can overlap these two as modeled, like I did when it was at the top. So what do you do? Well, I've seen a few techniques employed. One is to just put a step in there. Obviously this one's exaggerated, but just even a little step, enough to get more than one row of nodes where those two things meet. You are modifying the design simply for analytical purposes. It's not something that's physically there in the model. But if you think about it, that tends to be pretty common in FEA anyway. We're often simplifying structures and changing them a little bit to make them behave better as analytical models, understanding that the results in that area, say where these two things meet, may not be as realistic as they were before, but overall the displacements of the structure, the stresses in the plate structure, for example, and the deflection at the end would still be good. I've seen cases like this where maybe it was a weldment where the plate structure and the solid were going to be joined together with a weld bead. We do frequently discourage trying to model weld beads in FEA simply because you're oversimplifying what is a very complex problem. The weld beads tend to be a lot more complex than what we've shown here, but that doesn't preclude you from including them in the model if it's really only there to help join dissimilar element types like we have here, or even spread out forces and spread out stresses to avoid concentrating stresses at a single location. You can put your weld bead in there, and it's basically effectively putting in a step, right, where we can overlap the shell elements with the tetrahedral elements. I've seen stuff like this where we've got, in this case, I've modeled two plate structures. Both of them would be shell elements, and the bottom one is kind of like a row of gusset plates or something like that. I've seen the same thing done, but with line-based bar or beam elements that just kind of serve as structural supports to prevent that hinge behavior where the two meet. Just a few examples. Obviously, you might have to get more creative depending on your scenario, but don't feel like you're stuck with the geometry that you're given. You can change things a little bit if it means that you're going to get a good result elsewhere. Moving on to the problems that might arise when you're working with line-based elements. So here we've got our same solid block, but this time there's a line-based element joined to it. Let's look at the idealization for this. Okay, so basically that line has no geometric thickness. It's a sketched line in Inventor. You can use, in the case of Nastran and CAD, 2D sketch lines or 3D sketch lines. And basically you select that sketch and you tell Nastran that line is in fact a bar or a beam or a pipe, and what material it's made of. And then basically there's a cross-section input. Right, so what in this case it's just a round bar of 0.1 inch diameter, but you can have other cross-section shapes. Right, there's some common shapes in this wizard here, and you just plug in the dimensions and it generates the appropriate cross-sectional properties so that you get accurate deflections. It just assumes this cross-section is uniform across that line, and that's what we've got here. So remember that the line elements support all 6 degrees of freedom, but of course our 3D tetrahedral elements do not. So in this particular scenario here, I've applied a moment to the top of the beam structure, those elements will support it. They will rotate. Okay, but where they're connected, that rotation generated by the moment will not get transmitted. It will not get resisted by the 3D tetrahedral elements. So again, running this model, results in a failed solution, singularity detected, because basically that beam is just spinning around infinitely with no resistance to that movement. It's not a static problem. I can't get a solution. That applies even in a case such as this, where not a moment, but just a directional force at the top of the beam element. If you think about what that's going to do, it'll basically, if there is no resistance to rotation at the bottom of the beam, cause that beam to spin around, in this case on our z-axis, infinitely. So again, it's just a straight force, but that force is creating a moment, or would want to create a moment, where we've joined it to the solid structure, but because there is no support for the rotational degrees of freedom, we don't get a moment, we get rotation, infinite unresisted rotation. So how do you deal with that? Okay, in this model here, the distances are a bit exaggerated to show you what's going on. We don't have to have such large spacing, but what we've got here is our bar structure, which would represent something physical in real life. But instead of connecting it to our solid structure at one node, we connect it to 4 other beam structures, okay, that reach out and connect to the solid at 4 nodes. So by applying, say, a force or maybe a rotation at the top of this structure, in this case we put a force on there, any moment that occurs at the other end gets converted basically to translations. In this case, our force pushing off in this direction is going to result in a translation pushing against the solid at the top 2, and a translation pulling away from the solid at the bottom 2. Because the solid supports translations just fine, we will get force transmission, we will get resistance to movement, we will get a static solution. Okay, we'll just animate our displacements on this guy. And you see, in fact, we do have results. Now, Nastran has other ways of dealing with this that they've built in for us. Specifically, you can use connectors. What I did in that last model was basically build a connector out of bar elements, but you don't have to do that. You can use a feature that's built into the software. Okay, this is a different type of structure altogether. It's not something that you have to pre-draw. You might have to have some geometry in there to pick locations. So for instance, I had a sketch point on one end and a split out surface on the other end, and Nastran built the elements in between those 2 locations for me. In this case, it's something called a rigid connector. You can see all the little red lines connecting my single point to a bunch of nodes on the face. Rigid connectors do not deform, they do not have mass, they do not stretch or compress. They stay their exact same length and connect a single point to a bunch of points. So if I'm strictly trying to transmit a moment to the face of this block, I wouldn't be able to do that with one node, right? If I apply a moment to a single node, nothing's going to happen. But in this case, I'm transmitting that moment from one point to a bunch of points, basically converting it to translations at all the nodes on the face. Finally, when the bar meets the shell, or the line element meets the shell, that's where that drilling degree of freedom comes in, right? So set up here, I've got the line-based bar structure attached to my shell structure. Put a moment on the top. Again, those elements will support the rotation, but where it's connected to the shell, the resistance to that rotation would be in the drilling degree of freedom. So I'd need to make sure in my idealization for the shell structure, the very bottom there, that checkbox where it says include drilling degree of freedom, would convert these standard quad 4 or quad 8 shells that are drawn here into the quad R, so that they would support that drilling degree of freedom. If I had a scenario like this, in order to get good results, expected results, I'd want to make sure that box is checked, and that's pretty much it. So I hope that these very basic academic models will give you a sense for how the elements play with each other, and what kind of problems can arise, how to get around those problems. Obviously, real-world problems are much more complex, but the rules are the same. So if you're getting singularity errors at the, when you know you've got a mixed model with shells and solids touching each other, you know kind of where the usual suspects, where to look and what kinds of things you might have to address. Same things when you're connecting bars to shells or bars to solids. Basically, when you've got the same element type throughout, typically you don't run into these issues. It's when you start mixing them. So hopefully I made you aware and given you a better understanding of the rules. Good luck.